Afternoon, everybody. Only took me 3 times of saying that to actually do it. I'm mathing with the best of them. Yeah, we're gonna lecture today. Do a little lecture. I need to pull up my stuff, actually. I have some stuff pulled up, but not... funnily enough, not any of the stuff that I actually need. It's fine. Let's see. Honestly, the textbook that I use is so bad that I'm not even gonna call them out. Okay, I'll wait just a little bit before I start. But we got a lot to cover today. We are speedrunning linear analysis, like the title suggests. So we got some ground to cover here. This is gonna be like a best of highlights a little bit, more so than like it's a review. You know, it's like a cumulative review type beat. So we're going to start with differential equations, which, you know, I wouldn't start with, but since I don't have the linear up to where the linear and differential collide, it's fine to just start with some differential equations. Okay, so first thing about differential equations is in the same way that our normal equations have degrees, our differential equations are going to have degrees, right? And a differential equation is just an equation that has derivatives in it, right? So if we have a normal equation that's like x squared plus x plus 1 equals 0, our differential equation would be like dx squared over, you know, maybe dt, what is it? It's d squared x. Oh god, I'm already, you know, plus dx over dt plus 1 equals 0. That's just a differential equation, right? Nothing to be scared of. It's just some derivatives. And this would be a second order differential equation, just like this would be a second degree or degree 2 equation. So we're not going to focus on anything that's not first order, really. So we're going to start with first order differential equations. So first order. And there are a couple different modifiers, like adjectives, we can use to describe differential equations, right? We know of a couple. We know linear is one. We know ordinary is another. And those are the main two, right? So ordinary just denotes whether it is a derivative that's like d squared x over, there we go, d squared x over dt squared, or it's like a partial derivative, right? So if it's partial, then it's a partial differential equation. If it's ordinary, then it's regular derivatives. Funny how that works. For linear, it's a little different. Linear is a term that describes the way that our derivatives present themselves. If our equation is set up like d squared x, let's not make it a partial, d squared x over dt squared plus 1, let's not even do the other one, equals 0. This is a linear differential equation because we're not multiplying the derivatives together. All the derivatives are kind of by themselves. There's no, you know, there's no x here, there's no dx dt here, nothing like that, right? So, and also all of our derivatives don't have any sort of function applied to them, right? It's not like it's sine of x equals dx dt, or you know, square root of a dx dt equals x, something like that. Like that is not linear, right? So for a linear, we have to have a x to the n plus a, we'll do a1, a2, x to the n minus 1, dot 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 dot, etc., right? Equals something, I don't know. C, something else. F of x, right? Okay, so we know a little bit about differential equations, right? But there are some special cases that we might want to look at. There are a couple that you know, that are just kind of commonly used, I guess. And by commonly used, I mean my class uses them. So the first one that is liked for some reason, I don't know, it's pretty easy, is Newton's law of cooling. So Newton's law of cooling states that the derivative of temperature with respect to time is equal to the constant times the temperature minus the temperature of the medium. The temperature of the body minus the temperature of the medium, right? So it's just an object. Yeah, just an object. And we have this negative in here, right? Because like if our temperature is larger than the temperature of the medium, it's going to cool down. But it makes more sense to say it this way, right? We say the temperature minus the temperature of the medium, and then we kind of bake this number into it instead of saying like a negative k or something. So we'll learn a little bit later about ways to solve this when we talk about separables, or by using integration factor if our temperature of our medium is not constant, right? Because this assumes that this value here is a constant, right? Just assuming that like if we were to integrate this, well, I spoiled it. If we were to try and solve this, right? If our temperature of our medium was also changing to meet the temperature of our body, that would be a different question, right? We gotta think about more stuff. Another equation, let me think, what other ones have we got? There is an orthogonal trajectory equation, but that one we don't use an equation for. I really think Newton's law of cooling is maybe actually the only one. No, I lied. This is a classic one. F equals ma. Force equals mass times acceleration. So that's going to say that force equals, well, m times d squared x over dt squared, right? The second derivative of our position. Because, right, if we know that acceleration is the change in velocity, so it is second derivative of change in position. Second derivative for position. You can solve stuff with that. Not really anything else. Honestly, this one, really it's only Newton's law of cooling, because with Newton's law of cooling, it's kind of cool. Cool, get it? Because you can have a function, right, as your Tm, and that Tm would be in terms of little t, in terms of, with respect to time. But, you know, if you're, like, outside, and you're, like, you got, like, a hot cup of coffee, then your hot cup of coffee is not going to make the entire world hotter. So sometimes we just say that Tm is a constant, right, if you have a big enough room, or big enough volume of, like, material that the other thing's in. Newton sounds like a cool dude. That's a temperature joke. He was okay. He did kind of steal some of his work. Not gonna lie. Or, yeah, he gets credit for a lot of stuff that other people don't get credit for. But, you know, what are you gonna do, right? Okay, so we know a little bit about differential equations. We know about these two specific cases. Really only this one gets used, I think, other than orthogonal trajectories, but we're going to get to that later because there's a different way to do it that is kind of, it's easier, but it just is not the same way as doing it like this. So let's talk about how to solve differential equations, right? We can solve some differential equations. It can't be that hard, right? Like, what if we just had, you know, y prime equals a constant? Like, how do we solve that? You know, or no, not that. Y prime equals y. Let's do that. Because y prime equals a constant, we can solve that, right? That's just going to be, we integrate both sides, we'll get, you know, y prime equals a constant. We'll get y equals, you know, integral of some constant, y. And then y equals cy plus c plus some other constant, right? Or t. That should be t. My bad, gamers. But let's do a little bit more interesting one, because that's not really, I mean, it is a differential equation technically, but like, let's do y prime equals y. So we can think about this a couple different ways, right? But But since we kind of don't have any tools in our tool belt, we kind of just need to logic it out. So we know that the derivative of y has to equal its original function. So there are only a couple functions that ever like repeat themselves in derivatives, right? We've got our trig functions, so we got like sine and cosine. And we've also got our exponentials, right? So e to the x. Now these guys, they repeat. This goes sine, cosine, you know, sine, cosine. So it takes 2 to get back. But this one just goes e to the x, e to the x, e to the x. So in this case, if we wanted to find y would have to be equal to some constant times e to the x, right? So we can think about some differential equations like that. But we can also solve this with a different method, and that is by writing y prime as dy dx equals y. And then what we can do is we can separate the variables, right? So there is no x here. So what we can do is we can get all of the y's on one side, right? All the dy's and y's on one side, and then we can integrate. So what this will look like is, let's kind of do this. So we're gonna take the dy, we're gonna divide it over there. We're gonna get 1 over dx equals y over 1 over dy. And we're gonna flip the whole thing upside down. We're gonna get dx equals 1 over y dy. Then we're gonna integrate both sides, right? Classic little integration there. And we're gonna get x equals ln of y plus some c, right? So we want to solve this for y. We want to solve it explicitly. A lot of times differential equations, you might not be able to find an explicit solution and you'll have to solve it implicitly. So leaving it like this wouldn't necessarily be wrong, right? It's still giving you the right answer. But I think we can find an explicit solution here. We're going to raise both sides to the power of e. So we'll get e to the x equals e to the ln of y plus c. And we know that by our e rules, this will be like e to the ln y times e to the c, right? And e to the c, this is just some other constant. And we can call that c1. We can call it anything. We could call it like, I don't know, z, any number, alpha, beta, anything you want, really. But so what we'll get is e to the x equals y times c1. So if we move this over here, we're gonna get y equals c2. I'll just say it's c2, right? Because it could be e to the negative whatever. c2 times e to the x. And that is exactly what we got when we kind of logicked it out up here. Right? So that c can just be 1, right? That c could be 2 or whatever. It's not gonna, if the c is out in front, we're just gonna pull that down in the derivative. We're not gonna, that's not like a thing that builds up. Like if we had e to the 2x, that would start building up, right? Because of the chain rule. But when it's just out in front, it's no biggie. So we know that that derivative is gonna equal it. And that kind of makes like logical sense, right? Because when you take the derivative of e to the x, it's gonna be equal to e to the x. So through that, we can kind of see this one of the methods for solving differential equations, which is aptly named separation of variables, where you want to separate your variables, right? Have all of your x's or t's on one side and all of your y's or x's on the other side. So you can do that for a lot of different things. And once we get through this, I can show you like some more concrete examples, because I will start doing some examples, but I did want to just like lecture, because I thought, why not? I don't lecture a lot. But actually what we can do is come back to this Newton's law of cooling problem, and we can look at it through the eyes of separation of variables. So we're going to have d big T over d little t equals negative k times t minus tm. So in this case, our tm is just a constant, right? Our k is just a constant. So I mean, well, even past that, first step, we're just gonna factor that k, right? So we'll get negative kt plus KTM. So now we see that we've got something on this side, right, that has a bunch of stuff for us, and we want to get our KT on that side. Actually, I lied. We're not going to factor this out. That was silly. We're gonna divide by. We're gonna divide it because we want it on this side. And if we were to factor it out, right? And you get to this point. No, don't cut the entire layer. And you get to this point, and you're like, okay, what do I do now? And you try to move it to the other side. You can't really just move this over here. Like, you're adding it, right? That would be KT plus that. And then you can't integrate that. There's no, this derivative isn't attached to it, and so it's okay. It's a common mistake. I made it. But yeah, you just recognize that, and then you go, oopsies, I gotta divide by it. So we're gonna divide by this. So we'll do 1 over t minus tm dt equals negative k. Now we can integrate. So we're gonna integrate both sides. And now, if our tm was a function, this would be an issue, right? Because tm is we wouldn't be separating the variables, like this would be on the other side, but since tm is just a constant, this is just like a logarithm, right? So we'll have ln of t minus tm. On this side, plus c, very important, always remember your c's, equals negative k, and in this case, our extra variable is a t, right? So negative k t. And you could also say plus c on this side, but I just kind of lump all of the constants into one constant, just so I can skip that step. All right, so now we gotta do our classic little solving for big T here. So we're gonna raise everything to the we're gonna put everything on top of an e. We're gonna have e to the t, e to the ln of t minus tm plus c equals e to the negative kt. And we'll get c times, so this will be, right, you can imagine it's like this and that, so we'll have t minus tm times c. Actually, you know what, let's do this, let's have a little funky thing. Let me move this c over to the other side, and that can save me a little step here. So we'll put the c up here. So on this side we get t minus tm equals, now we can bring this down, right, and make it c1 e to the negative kt, and then we just solve. Look at that. So we just solved, I guess, kind of our second second ever differential equation, because we already solved one, and it wasn't even that bad. You just separate the variables out. You just put them on one side, put them on the other side. So the one thing you got to be careful about, right, when you're doing this is make sure you're not adding. You always want to divide stuff over. Otherwise, you're just not going to be getting real things. You're going to be making shit up. There are times when you can add, right? If you want to move something over and then divide, you can do that sometimes. But yeah, a lot of these will have little tricks. Like if there's any trig in them, there'll probably be some trig identity stuff. The integrals probably won't be very hard. A lot of them will probably be ln based. Some kind of like basic differential equations are this form, right? The c e to the negative like constant x or whatever. So it's pretty common. And this case is no different. But we can't solve everything with separation, right? Because we know that we have to divide by stuff, and we could have some pretty hard equations that we want to solve that aren't like this. And for differential equations, there are just equations that are for first order that you can't solve necessarily, right? We can talk about like when that's true or not for this next case. But there is another way that we have. Actually, so in my course, right, they cover two ways. There are a lot of different ways to solve these. There are a lot of very specific ones. Like, for example, there are Bernoulli equations, where you have to do something very specific by moving y's around and powers of things. And There's another type called by using phi integration, where it's kind of like partially integrating things and then setting them equal to each other and doing this, and it's kind of similar to the way you find potential functions from multivariable calculus. But yeah, we really only care about two types of things, which are the separation of variables, and the mu integration factor. Sometimes it's called other things. I was taught with the letter mu. I don't know why. The Greek one. Some people use I, which also makes sense, but I don't know, mu's kind of fun. So let's take a look at how we do this. Mu integration is kind of strange. There's a proof for it. I don't want to prove it because it's kind of a lot of writing, and I don't really know if that's super interesting, but it is a really good proof. I can tell you the basics of it. So what we want to do is we'll have a differential equation that'll be like a y prime plus like a2. We'll do c1. Linear algebraing it up. Plus c3 equals 0. And so with this, what we want to do is we want to get it into a specific form before we can actually use this method. And I think that it is. Just like totally make sure. One second. I'm pretty sure it's that. Yeah, no, I know what it is. Okay. So for the form we have to get this in is this. So we want nothing in front of the y. We want the constant in front of the y to be 0. So we're going to divide everything by c1. So we'll have y plus c2 over c1. Sorry, y prime. And we want this c3, whatever is left, on the left. So we'll have negative c3 over c1. And the motivation for this technique is that if you look at this, right, you have a y prime and you have a y. There's a couple places where you can have a y prime and a y, and one of those is in the product rule. So if you have a product that's like, you know, let's say it was x and y. That's going to equal, right, x prime times y plus y prime times x. So you can see this x prime and x comes up in that product rule, right? So that's the motivation for this. We want to find some function that we can multiply this whole thing by that lets us turn the left side into a product rule, because then that gives us a y, right? So it turns this y prime and a y into just one y. So the motivation for this integration factor is that the integration factor is the thing that will turn this side of the equation into a product rule. And it turns out, by whatever weird chance, that it's this. So mu equals e to the integral of, in our case, c1 over c2, right? So whatever is multiplied in front of this. This is sometimes called p of x, you know, there are a couple different proofs of this. And you can see that, like, this is a really weird little function we got going on, right? Like, this is a weird thing here. But yeah, it does the job. So what we do is we take this, we multiply everything by mu, so we'll have mu y1 plus mu c2 over c1 y equals negative mu c3 over c1. And this side is going to be transformed into product rule. So we're going to have mu, I think it's mu, is that right? I think that's right. We're going to have something, right? I'll just call it k, because I don't remember if it's actually mu or not. But ky prime, right? Because we put the prime out here when we have a product rule. And that's going to equal negative mu c3 c1. So because this is a prime, then we can integrate both sides, and the rest is history, right? So you'll get y equals, if you want to do this out, right, 1 over k. Usually it's negative, doesn't have to be negative, but negative mu c3 over c1. You sure are mewing a lot fits for a catboy? Yeah, maybe it was fate. Maybe it was called mew because it's like mew, you know? You like gotta like nya. Hey, if I don't mew a little bit in a lecture, if I don't go meow, meow, then what even is the point, really? I had a professor who meowed. It was great. It was very jarring the first time he did it, and it was really funny the other times. Cool. Yeah, so that's integration factor. And so a lot of, like, some people will just try and, like, memorize this last bit. I don't recommend that. This proof is not that hard to remember. It's not even a proof. Like, you don't have to prove the integration constant, you know, like, integration factor. You don't have to prove mu. Just, like, remember mu, and then just multiply everything, and then just see that it's a product rule. And then, like, divide and stuff. Like, you know, you don't have to worry about, like, messing it up, right? The less things you have to memorize, and the more things that you can, like, intuitively get, like, why they are that way, and what steps to take, the better, in my opinion. Okay, what else have we got? We could do an example, but I'll probably do some examples later. Okay, orthogonal trajectories, I think, is on the docket as well. So there's a way you can do orthogonal trajectories where you set, like, oh god, what is it? It's like you set the second derivative, d squared y dx squared, equal to, like, 1 over the first derivative negative, I think, is the equation. But there's a different way you can do it. Let's say you have this, okay? Okay, chat. We're gonna have a function, f of xy, and it's gonna be something. It's gonna be like, let's just say it's ax plus ax to the n plus ay to the n. Is it wrong to dream of your I don't know. Yes. Maybe. I don't think you can have a step professor. I think that it's just a professor. Well, 0. Okay. So the way that, okay, let me explain what orthogonal trajectories are. Orthogonal trajectories are, let's say you have, like, a function. That's a bad function to do an orthogonal trajectory for, my bad. Let's say you have a function, and we want a function to describe, like, every possible, that this function is a family of functions, right? So it's going to have some constants in it, because, I mean, we're probably going to be integrating somehow, right? Family of functions, and we want them to be orthogonal at every point, right? So we want, at every point, we want them to come out at the normal of this other function that we have. So I just drew a parabola. That's an ellipse, right? Not necessarily intuitively, but it is an ellipse. So the way that we can find that, right, is by doing that second derivative slope thing, or we can do this. So the first thing is to move. Okay, you want a constant on the right. This is called, like, finding the family of level curves. So what we're gonna do is we're gonna take, like, each little chunk of the function, basically, because as soon as we put a constant in here, this is sort of like the idea of the homogeneous plus particular, right? This constant is what's defining our actual curve. But this part is, like, just a free floating curve in space, right? Call that B. Okay, so we have a family of level curves, and what we want to do is we want to take the gradient of it, which is basically just a fancy way of saying we want to be able to find the slope of different directions of this function. So if we take the gradient, right, we're gonna do partial with respect to x, so that'll be an x n minus 1, and we'll do bn y minus 1. So now, this partial, we can do f of y over f of x equals, how do I do this? Let me remember real quick. I swear I remember how to do this. We do the slope, like, of the partial, and that's going to be our y prime. Yeah. So in the same way, like, we are kind of doing what the other method is, which is, let me find it. Where was it? If we look at the other equation, the 1 over thing, where is it? Where is it? Let me look. Oh, chat. Where is it? Where's our final trajectory? Oh, here we go. Yeah, dy dx, oh, okay, it's a little different, but like, it's dy dx equals 1 over f of xy. So what we're doing is we're just saying, like, the second one is equal to the first one. Yeah. It's a little different, but it is a little bit nicer. I'll do an example of one of these because I think that it's useful to do. So let's do an example with x squared minus y squared plus c equals 0. So this is going to look like, what? We've got y squared. I mean, if we solve this, I might as well just do it because I don't know what it looks like off the top of my head. We'll have negative y squared minus c minus x squared. Okay, everything's minus, so x squared equals y squared equals x squared plus c. We'll have y equals the square root of x squared plus c. Which is, I don't know, lines, I think, maybe? One of them is a line. But anyway, let's see if we can find, we don't need to know what the curve looks like to be able to find its orthogonal trajectories. So we'll have y squared minus x squared equals negative c. I mean, it's constant. We could just call it something else, but that's fine. So now we're going to take the gradient. So our gradient is going to equal 2x minus 2y, right? Just quickly take those partials. And now we're going to have negative 2y over 2x equals y prime. And now, let's write it like this. Now it's separable, right? So we'll do dx 1 over 2x equals negative 1 over 2y dy. And I've run out of space. So we're going to integrate these. That'll be ln of 2x 1/2 ln of x. Yeah. A little easier to do. And then equals negative 1/2 ln of y. So we do that. Get rid of the 1/2s. E to the ln of x equals negative e to the ln of y. Now we're really, x equals negative y. Right, so that is a line. It's a bunch of lines. I forgot my c. Fuck. Plus c. cy. I'll put it on the x. That makes a little more sense. Plus c. Plus c. There we go. It's important. It's important to remember your c's, because then your equation can be wrong. Right, so remember your c's, chat. I'm trying to think what else. We could talk about slope fields. We could talk about... solution curves. But those kind of suck. Might as well just do some problems then. Chat, I hope you're paying attention because there will be a quiz. But then we can get to linear algebra and it's a little more fun. Let me see, where is my thing at? I'm all over the place. Okay, here we go. Go back. Look at this. To the order, that would be fun. Let's see. Okay, let's do an orthogonal trajectory because I feel like that encapsulates like a good amount of things that we've talked about. Right, because we have the separables, we've got the orthogonal trajectories, we've got not integration factor. How's the semester treating you? I really want to graduate already. I'm on the quarter system, so quarter's treating me pretty well. I mean, it's only week 4. Yeah, week 4. I have 3 midterms next week. Math on Monday, physics on Thursday, chem on Friday. I'm kind of chilling though. It's actually really nice because I don't have to take any GEs this quarter, or I chose not to take any GEs this quarter. And honestly, beautiful for my mental health. Like I can just do math and like chem and stuff, and it's just like great. This is already in the form that we want, which is great, so we can just gradient this bad boy. And then we just do 2y over 2mx. These cancel. Equals y prime, so dy dx. Mx. And 1 over mx dx equals 1 over y dy. And we'll get ln of mx 1 over m. Just fucking do that instead. And then equals ln of y plus c. We'll put it on the x side because might as well solve it explicitly. This is kind of scuffed, but it's fine. E to the 1 over m ln of x plus c equals e to the ln of y, so that's going to equal y on the side. This is going to be c. Now the 1 over m, I think, is going to manifest in x to the negative m. I think. Because we put this on the exponent. So, oh shit, when I did this other one, did I do that? Oh god, it's so much bigger, I changed my pen size. Oh no, the 1/2's canceled, that's why. Oh, also the other thing was a circle. I don't know why I didn't see it was a circle. It's a circle though. Gonna stuff my face. Good luck with studying. You too. I assume you have studying to do. I don't know. It's like final season for semesters, right? Or almost. I don't know. I'm like gonna be fine. Like 2/3 of this is linear algebra, and linear algebra is like hella easy right now. It's just differential. I'm a little rusty at. Let's see if this is right though. I'll probably do some solution curves and stuff on Friday. Only one class. Yeah, this CS class in Major Dookie because the professor Being terrible at teaching, gave up on that one. Oh man, I hate it when professors be bad. My current professor, I like my physics professor, he's really good, but he was like, potential energy is the exact same thing as voltage, guys. And I was like, no, voltage is the difference in potential, but it's fine. The last one is just too much info. Just Braid's lucky enough to actually remember, to actually be studying and remembering the right detail. Oh no, that's the worst. That is actually so sad. Y squared equals C. We'll add a slider C, we'll add a slider M. Alright, so if we change M, it's gonna become an oval. Or a hyperbola, I guess. That's weird. I've not worked with hyperbolas, really. Is it a hyperbola if it's like... I actually don't know. Well, let's see if we got it right. Our answer would be cx to the minus m equals y. I don't think so, actually. Oh, sorry, c1. It'll be a different c. ax. Let's say, yeah, a. So if we set, like, it equal to... I don't know. Is that right, actually? If it's circles, it should be lines, right? Well, let's see. Ooh. I'm already so sleepy and I still need to study a bunch of stuff. It's okay. Because it's so warm out. Warm out and I'm sleepy. Do I have to add something? Did I forget to add something? Or is it just like my A? Can I step with 0.1 and it like looks better? It's supposed to be... Doesn't really look too orthogonal. Maybe it is. Let me see. Ortho trajectory form. It's probably right. No, I'll check it later. No, let's do one that I can actually solve. I don't know why I didn't do one that I like couldn't see the answer to. So I'm silly. Let's do like 15. No, let's 15's too easy. Let's do 17. I'll do 19. It's probably harder. If I can do one of these, then we should be chilling. Okay, so mx plus c. So this is a little different, right? We gotta make sure that that c is the only thing that is on the right. So y squared minus mx equals c. It's like, I love that I like know all the theory, but I just like can't do it. It's like so silly. Negative m, 2y. So of 2y over negative m equals dy dx. So we'll go for this. We'll do we'll do 1 over m dx equals. Ooh, this is a little interesting. 1 over 2y dy. So that's going to equal, right, negative 1 over mx equals ln y. So we'll do y equals e to the negative mx, I guess? Wait, I forgot my c. Damn it. Plus c. I always remember it when I'm doing c to the negative. Negative x over m. I just remember when I do my mu integration factors, but I forget for other stuff. Lol. Okay, let's see if that's right. I don't know, maybe it's not, maybe it is. Duplicate. Answers to odd numbered exercises. This is what was 1. 1. Uh-oh. E to the, what was that? What did we say? Oh shit, wait, 17? No, I was doing 19. Whew! Negative 2x m. Did I miss a squared in the original problem? Y squared. Oh, I did, yeah. 1/2. That'd be 2. Cool. Nice job, nice job, nice job. Okay. Let's do, I don't even know if I need to really, like, I mean, I can teach you guys about matrices and stuff, but linear, nonlinear. Oh, one thing we do kind of need to talk about is, I alluded to this a little bit, but there is a time where our mu integration won't work, right? And in general, our solutions for differential equations, well, this actually comes from, like, doing solution, like, curves and stuff, so I guess we can talk about that. Let me just do I think I can illustrate with an example better than explaining it. Let's see, what's a good one? Let's do, like, yeah, we'll do that one. I think I can maybe talk about that one. Okay, so when we have a differential equation, right, in a lot of the ones we've solved, like, even just take, like, y equals ce to the t. Let's say we had that. This equation, right, gives us a lot of different functions, right? That c is giving us a bunch of different functions. Really an infinite amount of functions, right? But in some cases, our solutions won't be valid, right? On a certain interval, for whatever reason. Because in the initial function, just like sort of how when you have a function that's like, you know, x equals 1 over the square root of y, or I should change that, y equals 1 over the square root of x, we have a domain error if our x is, you know, negative. We kind of have the same thing with our differential equations, but there's a little bit of a different way of looking at that. So let's grab a differential equation here. So we'll say y prime equals y minus x squared. So in this case, when we're analyzing a function, there are a bunch of different steps that we can take to check out what this equation will play like before we actually try and solve it, right? So for this one, like, we know it's not linear, right? Because there's an x squared. Actually, I lied. It is linear. But we might not be able to solve this. I think it's a mu substitution, so we can do it. But we want to see, like, what this will give us. So in the same way that that this function can be solved. Okay, that's a bad way of saying it. This is y prime, right? This is the slope of y. We can analyze what the slope of y is doing at different points, and we can figure out some different things about it, like where is the slope equal to each other? Where is the slope gonna have a limit to a certain value, like, etc. So our first step is to look for what are called equilibrium solutions. Equilibrium solutions. And this is where our function wants to trend towards a certain value and kind of stay at that value. So in this case, as x gets bigger this way, and let's say our y is equal. Okay, well, there's a couple other things we can talk about. There's something called isoclines, which are just lines where the slope is equal to each other. So like in this case, when we have y, when we have x a constant number, wait, that's not, I don't even know if we have isoclines here, right? Because an isocline would be like we have a bunch of slopes that are all like here, right? So if y prime was equal to y, then it wouldn't matter what x we were at, our slope would stay the same. But this one, we have two different things changing, so we don't have isoclines. So we just kind of have to figure out some different things. One of the questions we can also ask is, are there any restrictions, right, on this function? So what we look at is y prime, is our function right here that we're given, is it continuous, right? So like if there was a square root, that wouldn't be continuous. If, you know, there was some denominator, if there was a whole or discontinuity or whatever, that would be non-continuous, or discontinuous or whatever. But we're pretty good in this case, right? You know, our end condition might be a little weird, right? As x gets really big, we're gonna go to negative infinity, but so normally we would look for, like, for the first step, the 0th step is to check for discontinuity. And the second step we can also check for is we need to make sure that f of y, so this with respect to y, is also continuous. Well, I guess we don't have to, but so when we're looking for discontinuity and we're looking for the discontinuity of the second derivative, we're looking for existence and uniqueness of solutions, right? So we're trying to find a way to describe where and when solutions will exist. So let's say you have a discontinuous function, right? That's like a square root or something. Your solutions can exist, but they might not exist like in the negatives, right? So you would then set an interval of validity, which is just a fancy way of saying where your solutions are valid, where your solutions would be valid, right? An interval of validity where your solutions will be valid, and then your solutions will work in that interval. So all of this is sort of to like just kind of set the stage for us to find solutions, or if we can't find solutions, then think about what they could be, right? Because sometimes we can't solve differential equations. Yeah, so we check for discontinuity in f of xy and in fy, and in this case, they're both continuous, right? So now we get to look for some different things. We can say when we'll look at y prime positive / negative, right? So it's positive when if y is positive and x is negative, so over here it's positive. If y is negative and x is negative, wait a second, no. Oh, this is a little interesting. So if y is greater than x squared, then it's going to be positive. But if y is less than x squared, it's going to be negative. So this is kind of, if we have positive, y has to be, okay, this is kind of going to be hard to draw, I think. But we can still try. In this case, if y is negative at all, there's going to be a lot of negative, okay. And there's going to be positive maybe kind of along this line, I think we can say. Because like when y goes to infinity but x stays small, we'll go to infinity. Yeah. We can also look at the second derivative. So when y double prime is positive or negative. So that would be 1 minus 2x. Can I do that? Maybe I can't do that. Maybe Maybe y minus, oops, y minus 2x. Something like that. When that is positive or negative, I think it's 1 minus 2x. So then when 2x is less than 1, the concavity, right? The concavity is, so in here the concavity is concave up, so like this, but then outside it's going to be concave down. I mean, we can start drawing some stuff, right? So you can mark it out. Maybe I'll do a little bit of it. So when y is 1 and x is 1, it's a good one to do. It's going to be 0, so it's going to be flat here. Now with these, like, you can actually, with something like this, you probably won't, like, I probably won't be doing this, you probably won't be doing this when it's like this dense, I guess. You'll probably have isoclines and a bunch of other stuff to check for. This is not really the best. This is more, I think this is more for drawing the solution. Yeah, no, it's just showing solution curves. Oh, that's funny. It's saying that you have to get a computer to plot it. So maybe we definitely should have not chosen this one. Yeah, we know the slope is going to be like, going to be getting more and more positive, right, as we go up, so something like that. And then here, this will be like, when x is like 2 and y is 1, it's going to be like kind of negative. And then eventually it'll kind of turn more positive along, wait a second, y is less than x squared. It'll be, okay, this is kind of weird to think about. Along this parabola, there's going to be zeros. And then above this parabola, it's going to be going up, increasing. And below it, it's going to be going down. Right? Like this. So this parabola is 0. And like in here, another 0 there, and it's positive. So it'll be like, you can like go, let me draw in a different color. This is a bad example, but like, so like you can go up, you can go like up and then down, you can go like down. And actually, to our credit, this is actually what it looks like, which is kind of impressive because, okay, they might not all pass through the origin, right? Like some might pass through up here, some might, you know, go this way. This is pretty impressive because like, normally you wouldn't be doing something with this complicated, but yeah, normally you'd have equilibrium solutions. There are no equilibrium solutions, right? There's no place where like y goes, where that equals 0. Well, I mean, the equilibrium solution is that parabola, right? But I digress. Yeah, so for an interval of validity for this one, it would be everywhere, right? Because there's nothing that's stopping our solutions from being valid. They're all continuous and they're all like chilling out. There's nothing that like gives us a 0 on the bottom or like gives us a complex number or anything nasty like that. Alright. I don't know, should we do some linear algebra? I feel like some linear algebra is necessary. Cleanse the palette. Is there anything else I was going to talk about with differential? Orthogonal trajectories? No, those are fine. Mu integration, we did that. Interval of validity, yeah, that was even a little extra bit. I don't know, I think that's pretty good. I think that's pretty much all of congratulations, chat. All of differential equations. I'm kidding, okay, I'm kidding. Yeah, there are actually only a couple things to remember. Oh, you might also need to know Hooke's law. Who knows? Hooke's law is also a differential equation, but like, fuck Hooke's law. Sorry, all my homies hate. Never mind. Actual genuine speed run through matrices. Okay. Okay. If you're a programmer, you know what an array is like, right? It's a bunch of numbers in here. You know what a 2D array is. It's when you add an array into each position. Congratulations, you made a matrix. Matrix is a bunch of numbers in rows and columns. I'm just gonna put zeros in here, I don't care. It's a bunch of numbers they're in there. You got row, 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 column, 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 column. You write matrices row by column, okay? Number of rows by number of columns. Do lots of stuff to matrices. You can add them together. You could say like 1, 2, 3, 4 plus 1, 2, 3, 4. And the way they add is you just add each element, right? So that would be 2, 4, 6, 8. Who do we appreciate? Matrices. You can multiply them. 1, 2, 3, 4 equals 2, 4, 6, 8, right? Just want to flex a little bit. This means that 2 by 2 and any matrices like these, right? Any matrices you can add are a closed subspace of Rn or whatever number of matrices you're in, because it is closed under addition and scalar multiplication. But we're not going to talk about that right now. We're talking about matrices. What else can you do with matrices? You can take a system of equations, right? 2x plus 3y plus 4z equals 2. 8x plus 5y minus z equals 3. And you can turn that into a matrix, right? That means we're going to take all the constants and we're going to put that in a matrix, right? So really easy. 2, 3, 4, 8, 5, negative 1. You line up, you make sure each column is one variable and each row is one equation. Some people write a line here, but we're going to put the constants on that as well. You don't have to put a line there. I don't really put a line there. That's called a partition if you do that. Fancy word. Another fancy word, this is called an augmented matrix. If you have just a matrix with the coefficients, guess what it's called? Coefficient matrix. Great. Wonderful. It's called augmented because we augment, as in tack on, the coefficients to it. Cool, congratulations, you already know linear algebra. Now, why do we do linear algebra? Great question. One of the reasons we do linear algebra is because we want to look at a lot of data. We have a bunch of data and we want to get information out of it. We want to figure out relationships between different things. We want to figure out what are they doing? What are they doing in there? I don't know. We're going to figure it out. We can also use it to solve systems, right? That is sort of the same thing, but we can use it to solve systems. So we can do different things to this matrix. If it is a system, there are a couple different things that are allowed that we can do, and that will allow us to solve the system. So what we want to try and do is we want to get this matrix into what's called reduced row echelon form, which is basically a fancy way of saying, hey, here's a matrix that looks like this. We want to get it to that. So basically what we want to do is we want to have ones on the diagonal from the top left down as far as they can possibly go. And you only want to have ones in that column, right? So if you have a 1, right, we can't have a number here. That can't be E. This has to be a 0. And that is called reduced row echelon form. Then, what that says is our numbers over here, if we get it to completely reduced row echelon form, like if we had, 1, 0, 0, 0, 1, 0, 0, 0, 1, B, C, D, these numbers right here would be our solution, right? This would be X, this would be Y, this would be Z. And the reason why is because if we were to go back to our matrix form, right, we would see, okay, there's a 1 in this column, X equals B. There's a 1 in this column, Y equals C. And there's a 1 in this column. I don't know why I didn't write A. Z equals D. Cool? Cool. So how do we get there? How do we do things? How do we turn numbers into other numbers in a matrix? There are 3 operations called the elementary row operations. You do them to rows. You can also do things to columns, but that is a little trickier, and we don't really do it that much. Columns come in more when we want to do stuff with the determinant, because you can pick different columns to do things. But first thing we can do, add 2 rows. So we can do like R1 plus R2. Second thing you can do, move or switch 2 rows. R1 switch with R2. Third thing we can do, multiply by a constant. CR1. Those are 3 things we can do, right? And if you know anything about subspaces, this kind of goes to the same idea, right? This is a subspace. If we multiply it by a constant, it's going to still stay in that subspace of the same matrix. That's a weird thing to say if you don't know what that is. It's fine. Okay, so let's try and reduce this then. Okay, we're gonna have 2. I'll just write it down here. 3, 4. No, I don't want to write it again. We're just gonna jump right into it. Okay, best way to do this, kind of formulaic way to do this. Fuck, this is gonna have fractions. I'm changing it actually. 2, 4, 6, 8, 1, 3, 9, 12. That's our new matrix. We're gonna, okay, so in this case we want to get a 1. The fastest way to get a 1 in the top left is to switch these, right? 1, 3, 9, 12. 2, 4, 6, 8. Fastest way to get rid of this 2 on the bottom, row 2 minus 2 row 1. That 3, 9, 12. So 0, right? 4 minus 6 is negative 2. 6 minus 18 is negative 12. And then 8 minus 24 is negative 16. Cool. Now we can divide this by negative 2 because we want a 1 on the bottom, right? R2 divided by 2. 1, 3, 9, 12. I like how my matrix is just getting more and more squished as time goes on. 1, 6, 8. And then all we gotta do is we just gotta do R1 minus 3R2. And we get 1, 0, 0, 1. 9 minus 18 is negative 8. 12 minus fucking 24 is negative, wait, what the hell? Did I do that right? 9 minus 18, yeah, negative 8. Negative 9. There we go. And then 12 minus 24 is negative 12. Cool. So let's take a look at some things. Every 1 that's only 1 in the column, you get to circle that. Those are called pivots. These can tell us different things about a matrix. But we're not going to talk about that just yet. We can keep them circled though. This tells us how many free variables versus, I guess, bound variables we have. In this case, because we have 2 and we have 2 variables, all our 2 variables are free bound variables, right? They are defined within this matrix. If instead, for some reason, we had a 0 here, we'd have 1 bound variable, and then, because we had 2 variables, 2 minus 1, 1 free variable. But we don't, we have a 1 there. So our equation is going to look like this. Y plus 6z, sorry, equals. So now, oh, I lied. We do have a fucking free variable. Pivot. We have 3 variables, not 2, but that's because we only had 2 equations, so we were never going to be able to have a fully defined system. So what we want to do is we want to solve for each variable, right? So classic little algebra move. Y equals 8 minus 6z. We see that z comes up in both of these, right? And we know that we have 1 free variable, so z is our free variable. We can call z anything. I'm used to calling it r because I call my free variables rst. I don't know why. I just do. So now we can write this out as our solution set. 12 plus 9 r, 8 minus 6r. And if we split this up into a linear combination, which is just a fancy way of saying 2 vectors that are added, right? Because we know when we add matrices, this is just an addition. We can say this is the vector 12, 8 plus the vector 9, negative 6, r. And so what this is telling us is that our solutions for this system are a line. And I'm saying, Damie, what the hell? What the hell does that mean? Well, we have a point, and we have a direction, and we have a slider, right? So we have a point, we have a direction, and we have a slider that can go anywhere from that point on that direction. And that is a line, baby. So one thing we can do is talk about linear independence of the columns, right? So actually this is a great example of linear independence. These two vectors, right, these are linear independent, and all that is saying is that they are not, you can't express these vectors in terms of the other vector. And this kind of makes sense, right? Because when we kind of crush this vector down to its basest form with the 1 in the front, in this matrix, in this setting, we see that this, right, there's nothing here. There's a 0 here. There is no number we could multiply this vector by to make this a 1, to add these together. In the same case, there's a 0 here. There's no possible way that this vector multiplied by, or like, you know, added, any of that could possibly make that 1. And that's why when we row reduce to row echelon form, we have only a 1 in the column, right? That ensures that if we have leading 1s here, we have pivots here, the other vectors just can't add, right? So if we have like 1, 2, 3, these are linearly independent because there's no way, even if you added like these two together, right? You would get 1, 0, 1, 4. That's not, there's nothing here because we got rid of all the stuff there. So it's kind of really beautiful how we can see that these vectors are telling us different information. What else? We can do inverse is kind of dumb. It's not really worth it to talk about inverse, I don't think. I can talk about, hey, you're back. How was food? How were things? Things are good. Just doing some matrices, doing some linear algebra. It's a lot easier to speedrun the basics of linear algebra than it is to speedrun differential equations. Orange chicken? Oh, I'm gonna get that for dinner. I'm actually gonna do that right now. What if I got it now? No, I have to stream. Got distracted. Order the orange? I'm gonna order the orange. It is not, like, it's an on-campus place that has orange chicken, so. I don't have to go far to get it, so I'm probably I'll order it like 6 when I finish streaming. Let's see if they still have it. I did not get Deep Rock Galactic, and the reason why is because I bought a bunch of stuff this month, and I feel too bad if I spend too many things in 1 month. Teehee, smiles. I'm a frugal cat boy. Well, it's also because, like, I don't really have the I don't have the steadiest income. I guess I shouldn't say it like that, but I don't have, like, a day job. I'll miss a sale. I'll buy it next month. I'm also, like, I bought another game this month, so, like, I've been playing it. I've also been playing a lot of Minecraft. So, like, when I like, have a game, I try not to buy, like, multiple games at once, because I get really into a game, and then I, like, forget about the other one, and then the newness of the other game I bought, like, kind of wears off, you know? But I do want to play. It looks really cool. I actually really also want to play Astroneer, because I think it came out of beta. Yeah. Those would make good stream games. Oh, actually, it would make a really good summer stream game, because, yeah, I'm gonna definitely stream more, like, games and project-y stuff this summer. And I think I'm gonna try and switch to doing lectures, like, over YouTube. I'm not really sure. Like, lecture, like, stuff like this. I actually want to do lectures. Summer Damie. There's a lot of cool stuff that's gonna happen this summer. Beach episode hype. Maybe beach episode. If I could figure out how to do that in a way that makes sense. Maybe. Maybe. Bring the tanning oil. I will say, so this vector here, so we solved the system, right? And just because I was lazy and didn't write 3 equations and just wrote 2 instead, we got this free variable, this r, right? So we know that this is a line, and this means that that these vectors aren't there's a way to cover the space. How do I say this? No, this is a solution set. This isn't the same thing. Oh man, while walking back, I realized how much math I haven't done and forgot. Kind of ashamed at letting my math muscles get weak. Yeah, I think I wanna, well, I don't actually know if I talked about this on stream, but since I'm kind of winding down, I don't think I'll be lecturing for that much longer. Like, one of my main, goals for, like, math and, like, teaching in general is I really, really want to make, like, a game, like a video game, that teaches people calculus. Because when I was a kid, there was this game called Dragon Box, and it was called Dragon Box Algebra. They also had one for geometry and stuff, and it was this little dragon in a box. He looked like this. And you, on one side of the screen, there was like a bunch of stuff, like a bunch of objects, like fruits and like little creatures and things. And on the other side of the screen, there was also stuff, different stuff. And what you were supposed to do is you were supposed to get the dragon alone so that he could eat all the stuff on this side. And what it was doing was it was like teaching you algebra without teaching you algebra. They would like teach you the rules, right? So they would have like a bubble is what they called it, where like you would have like a thing, you know, times like 2 things that are stuck. Well, they would have like things that are stuck together, you know, and that would be like multiplication. And they would have like a bubble, and you know, it would be like divided by something, and it would be like, oh, you can't break the bubble until the thing on the bottom is gone. And it's like, yeah, when you're doing that, it's like, sure, it's rules like a game. Like you're tricking your mind into just thinking, oh yeah, you can't break the ice until it's a bubble, right? But like, and you break the ice by moving, you know, multiplying this to this side, or by moving this to this side, right? But like, you're actually learning algebra. Surprise. And I really want to do that, but with calculus. So like have a very abstract, like fun version of like calculus, and also probably like linear algebra and stuff like that. And I really want to make a game about it. Because I think a lot of people... Give me a Calc 1 and 2 and linear algebra gotcha game. Oh my god, that'd be awesome. That would be so fun. I really want to work on it. I think I got a little not disenfranchised. I got a little burnt out on games, because I worked on a game all of last year for a project with a friend, and it was a lot. Like, it was a really big project, and it was like all hand drawn, so it was very taxing, because I was the artist for it. And I want a bunch of Damies as SSR Husbandos, Beach Davy, R Davy, Professor Davy. I could do that. I could have a cameo. It wouldn't be a Damie themed. I mean, I guess I could do it Damie themed, but like, I don't necessarily want it to be like Damie themed. You know, I want it to just be like a game that anybody can pick up and play. But that's like really funny. I should do that. There's so much. Oh, there's so many cool things I have planned that like I really want to be able to do right now, but I just kind of have to wait because I'm really busy. There's a lot of cool chat stuff I have planned, like interaction stuff. And also, yeah, I mean, I want to try and like branch out more and grow my audience a little bit. Try and get more people around. That's my one of my goals. But it's just because I don't stream consistently. I mean, it's a lot better than it used to be. I used to just have, like, a lot of streams where nobody would show up and then I would be sad. But yeah, not to be depressing. I don't really worry about numbers that much. Ha, I do. It's my job. But I think just like having more like, because I feel like Damie, like me, like if you want to watch my streams, you have to catch me live, you know? And I don't really have like any sort of edits that I do of stuff or like, you know, so I want to kind of, it was pretty quiet sometimes. Yeah, I kind of like that though in some ways. Like, I find it good that I can hold my own, you know? Like there are some streamers who wouldn't be able to stream without a chat. But I find it nice that I can just kind of like actually, like it makes me a better lecturer. My mic became a whole lot better. It did become a whole lot better. I'm glad. It was because I was a laptop streamer for a while. I miss my PC so much. I could have so much. I could have all my redeems and stuff still if I was on my PC. But that won't happen. Well, it'll happen over the summer. So I'll be really good Damie for like 3 months. And then we're gonna go back to like a little bit mid Damie. I think I'm gonna wrap up soon. I'm trying to think if there's anything else. I could talk about inverses, but like, who needs inverses? How many more years till you're free and be able to become a full-time brain tuber? I'm not gonna be a full-time brain tuber. I'm gonna be an engineer. But I do definitely want to stream, like, I mean, if it was a viable way of income, maybe, but like, I need more enrichment, you know? Like, I need to be able to work on, like, parts and stuff. And, like, even though my undergrad is, like, just started, basically, like, it's so fulfilling for me to, like, do design and, like, think about creating and manufacturing stuff that I'm like, I don't think I could ever not do that. But this summer, I think, is gonna be, like, more of a jaunt into like what I want my content to be. And what it will probably, because I think about like people who graduate like really soon, and I'm like, why do people do that? I guess technically it's my like 2nd year streaming, but I don't think I'll stop. Unless no one really cares. Lol. But like, I think I'm gonna try and branch more into projects. I was trying to branch out into projects originally, but I really didn't think that people wanted to watch stuff that wasn't, like, funny. And it got to a point where I had a bunch of, like, funny project ideas and stuff, and then I just, like, couldn't think of any more. And a lot of my projects now are, like, they're just, like, cool. They're, like, cool, or they're, like, interesting or useful. And once I found, like, the side of YouTube that was actually people making useful, cool-looking things and people liking it, I was like, holy shit, wait, I can just do that, and, like, then I'll never run out of stuff to do. So it'll probably be like that. But I really like streaming. I'm not gonna, like, stop streaming. I think about, like, Wayne Radio, and how he's, like, super popular, or not pretty popular now. Like, he has a pretty big audience. But, like, for a while, like, he just pretty much just streamed to his friends, you know? And, like, a very small audience, and, you know, he worked his way up, so that's what I'm trying to do. I feel like this is, like, the first year I really started streaming, because I streamed a long time ago, but I streamed, like, no mic. I streamed, like, you know, PNG tuber, and I think a lot of that was, like, my, like, trying to, like, figure out how I wanted to best, like, teach people. But, like, also, like, in terms of teaching people, like, I actually started, like, getting paid tutoring jobs and stuff. Like, I've grown a lot in that sense, too. Inspiring chat. Yeah. I don't talk about it a lot, but I feel like it's good to have out there sometimes, because as an indie VTuber, and as a very small indie VTuber, I feel like people don't talk about it like that. I feel like people talk about it like, because there's almost no, well, I don't want to say that. There's a lot of people who, like, like do variety content, who do like gaming and stuff. And there's not a lot of people out there who are trying to like do really niche stuff, you know? And so I don't hear people say like, you know, like people's viewers usually grow, like I would say faster than I think mine have, but it's just because I'm so niche. But I like that, you know, I'm sticking to it because I do this because I like it, and I do it because I like helping people and like making math content and all that. So it's worth chat. You guys are the real ones for sticking it out through all my linear analysis, my math stuff. I hope I make stuff that's interesting at least, or fun or comfy or whatever. Anyway, I think with that I'm gonna. You like being here? Oh, yo! I like you being here too, Egg. That's so kind of you. It always amazes me, like when people say stuff like that. I'm like, God damn, because nobody really like. I was very I was pretty not reclusive. That's not the word. I was like not like a loner. I just was like very introverted, like for a lot of the time growing up, and yeah, so not a lot of people like really gave me any sort of compliments past my like academic achievements. And even then it was sort of just like, wow, you're so good at things and it must be so easy for you. And I was like, sure. Yeah, definitely easy for me. But so yeah, it means a lot when people say that kind of stuff, because I don't hear it a lot, you know? And it's nice to know that when I come out here, I'm not just like meowing into the void. I got a good ass voice. That's so nice. I hated my voice for a long time. That's nice to hear. I hope it'll get even better when I like get better, because I still feel like, I don't know, I got a ways to go with my audio setup. I got a ways to go with like my whole stream dealio. Hopefully it can be like really nice, you know what I'm saying? So nice, thank you. I'm gonna order orange chicken right now, actually. Let's do it, chat. This summer I gotta get back on that crush grind, actually. That's all that's... It's like I like save up for like this big reveal. I'm like, guys, there's so much stuff happening this summer. I swear it's gonna be so monumentally different. I turn into a crush streamer only. Oh, I miss Crush. They had a winter event. Did I stream the winter event? They had a winter event. I was trying so hard to get it. I was so close. I don't think it was possible without paying. I'm gonna be honest. I was kind of mad about that. One day I will figure out how to mod Crush so that I'm in Crush, okay? I don't care about anything else. I don't care about anything, any other dating sims. I don't care about anything. I need to figure out how to mod Blush or make my own version of Blush. I was coding a version of Crush. You might see something in my Steam. Did you get? No way. Did you gift me Blush? It's the husbando version of Crush. Yo, oh my gosh. You just typed Crush. Is it another game? I have played it on stream. Oh my gosh, thank you. I'll have to play it. That's so awesome. It's like a bunch of hot boys turned into animals, and also one of them is a blatant ripoff of Markiplier. It's really dumb. It's really dumb, but it's really funny. It has voice acting too. Yeah, I could be in Blush. I'm already a Catboy. Like, I'm already there. There is a stage where they turn into like boys with animal ears. You're level 50 plus if I want assistance? Oh my gosh, I'll have to check it out. Let me think about when I have time. Tomorrow I might have time. I'll text you. Or, I don't know, maybe I kind of want to like show like first impressions on stream. Maybe I'll save it for, maybe I'll do it next week. Maybe I'll do it next Thursday. Because I think, yeah, I'll have my physics midterm. I'll have math quiz that I'll probably review for, but it shouldn't be that hard because linear algebra, I know that. Yeah, you know what? Let's do it next stream. We can pop in VC or something. Or like just be in there. Oh, check it out. Thank you so much, dude. That's awesome. Oh man, that's so nice. Okay, I'm gonna go. I have to eat and also best wishes to my orange chicken. Wait, let me show you. Let me show you guys. Let me flex a little bit. I just got new PLA. Well, not just got it. I got it and then I needed to test it to calibrate my printer for it, and I printed this little calibration dragon, and it's really cute. And I think I'm gonna make it my like actual calibration model. Because I was gonna do benchies, but like, they're not that, I don't know. They're cute, but like, this little dude is so cute. And, okay, the angle of it hides how bad the overhang is. I'm glad you guys can't see how bad the overhang is. I need to definitely change my, I think it's my fan settings to fix the overhangs, but I have to do some overhangs in this print that I'm doing, and it's for like a client, so like let me show you guys. Where's my, can I just like copy and paste this in? No, I can't. Browser, yeah. Let me grab the link to this. Image link. Show you guys. 1 second. This is like a lot of effort just to oh look, there's someone, Rev's handwriting. That was from a while ago. Remember that time where you guys were all dunking on me for my handwriting? That was funny. Somebody else was dunking on me for my handwriting recently, it's fine. This little guy, look at how cute he is! You can see my like, my silly little desk mat in there too. You kiss it? I know, right? Isn't he so cute? It's like, okay, there's some stringing on the antlers. Just a little bit though. The detail on the scales is like bad. But I think I just need to change my layer height then. Not really that much of an issue. Nice keyboard. I really need to clean it like really badly. I also was changing out all the switches, or I was lubing like all my switches and stuff, you know, keyboard things. And then I just like, I was doing it with a friend and he was helping me take them all out because they were in there like really tight. And I just like couldn't get them out. Like I don't have great hand strength, and then I had to just stop. So I did the top row and they sound like better than the rest of it, but it's just the top row that sounds better. So yeah, it's kind of rough. Yeah, this little dude, he lives on my printer now. He's my printer totem or whatever. I also have my my fuck yes joint that I finally made. That joint that I was making like 80 iterations of that I made on stream. Like I made on that one like really scuffed cursed stream that one time with lichen. I finally finished it. It still makes me mad that like it's not good. I realized that I can do a mirror modifier on it to make it better. But, you know, Ethernet he's coming along. Imagine blazed up with red eyes. I've never smoked weed. It smells too strongly for me. I would like have to, like, people in my dorm do, and like sometimes it will just come in, like if I have my window open, just like the smell of them, like, God, everything sucks so much right now. I've got a little catboy nose, you know? It smells so strong. That's, strangely enough, like the main reason. Although I don't really do substances, I guess. That's the best way. I don't really drink. Also not old enough to legally drink, so that's part of it. Maybe we'll do it. We'll do a Damie 21 birthday stream, right? Down the line. I'm almost 20, not almost 20. I'm 19 and a half. It's crazy. Just a little guy though. It's weird. I need to be 20 already so I can just say I'm 20, and then like life. I feel like it'll make more sense. I feel like it's weird to say like when you're 19 and like you're ready to be 20. If you do get to get something fruity, those taste nice. Yeah, I would definitely be a bitch about like the taste, I'm not gonna lie. It's funny, I'm on the older side for like my year, but still pretty young. Don't really think about it that much though. Alright chat, I'm gonna head out. We'll play some games next Thursday that Egg so generously gifted me. That was really nice of you. I'm very much looking forward to that. So yeah, I'll see you guys later. I hope you enjoyed the little mini linear analysis speedrun. Maybe you learned a little bit. Differential equations mostly, but that's because I did differential longer ago and there's more of it. And linear algebra is pretty cumulative, but you know. Okay. See you guys later. Have a good night.